Ever thought how your laptop or phone saves the battery but still runs fast thanks to something called power management unit? It's like the chip's power manager, deciding which part should stay on, go to sleep, or chill to save energy. Inside the chip, there are power domains, basically the zones that can turn off when not needed. And to tell the design tools how all these power control works, engineers use UPF. Then comes the special helper blocks, level shifters that let different voltages talk, isolation cells that stop errors when some parts turn off, and retention cells that keep memory safe even when the power is gone. It's all about balancing power, performance, and area, PPA, so your devices can run longer, faster, and better. So stay tuned till the end of the episode to know more. Hey guys, welcome back. In today's episode, we are discussing the below points. First, we'll do a general introduction. Next, we will talk about power delivery network, its significance. Next, we will jump into the concept of power domain. Next, we will explain the power management unit through infographics. Next, we will talk about the standard cells available for power management. In the same context, we will talk about the power switch cells, isolation cells, and retention cells and level shifter cells. So these are the standard cells used for power management. Finally, we will talk about the power management methods. This is the menu for today. Without any further delay, let's begin. Introduction. In SoC, more and more transistors are getting added and pulling to the risk of very high power dissipation in a die. So as per the Moore's law, many transistors are getting included in a chip as we proceed towards a lower technology node, and it causes the high risk of power dissipation. In the contrary, customers look for portable handheld devices having long battery life after a single charge. So you are quite familiar with this kind of handheld devices like your smartphone, PDAs, etc. Chips in mobile and handheld devices, advanced power management systems that can improve efficiency without sacrificing the performance. So just to fill the target that the battery life should be higher, we have power management systems inside the chip. This is done by adapting to the demands and constraints of particular workloads. Mobile, IoT, or handheld devices usually often driven by unpredictable sensor or a user input. If it is a wearable device, it is monitoring like a smartwatch, it is monitoring your maybe your heart rate or something. So there is a sensor, right? Or user input. In case you are using a smartphone, the app you are operating by hand, so it is your user input. So these are the typical examples that you find day-to-day life nowadays. These have especially bursty workloads, right? Bursty means it has a lot of things to do once it is triggered, with short period of high compute demand. That means whenever you trigger it, it demands for high computation through the processor, followed by long period of inactivity. This is the nature of the devices, whether it is your smartwatch or it is your smartphone or any other wearable devices, or maybe some medical devices that you are using. So there is a trigger. That trigger triggers a lot of activity in a burst, right? And then once those things are done, it goes for a sleep for a long time. So this is the typical type of nature that the devices have. Modern VLSI circuits integrated with a separate power management unit whose function is to manage the power distribution in the die efficiently. That means whatever we have talked about here and above, all these things should be manageable by the power management unit. This is the role of the power management unit we are having in modern days chips. So we are done with this particular slide. Let's move on to the next slide. Power delivery network, the significance. Here we will discuss about the significance of power delivery network. Now, what is a power delivery network? We will explain it through infographics here. The power grid in ASIC provides power to turn off or turn on any VLSI chip. So let us see it pictorially, that means with infographics. Here is our chip. So this is here our silicon lies, right? And here it's the boundary, right? You know it. Here it is drawn in with color, right? Let me point out up parts of it. So this is the power ring, right? This one is the power ring, and this is also the power ring. So it will say this is VSS, or VDD, say the another could be VDD, or vice versa. Whatever kind of things you have, you can have this as a VDD and this as a VSS, right? So these are power rings. That means this one, right? Is the thing that we are talking about here, or this one. Now, power strips are the sub lines which take up to the center of the silicon, right? This is a power strip and this is also a power strip. So this is a green color power strip and this is a red color power strip. So one is VDD, another one is VSS. Next, we have the IO pads here. We have IO filler. Here with the picture, you are getting familiar with the entire chip, how the things are there from a bird's eye view. Here is a corner cell and here is the core. This is where the silicon, we call it core. Power delivery network carries power towards the leaf cell such as standard cell, IP blocks or macro blocks. So you can see these power strips gets further subdivided into power strips. Power rings are subdivided into power strips and those carry the power up to the leaf cells, which may be standard cells, which may be IP blocks, which may be macro blocks. The power management unit resides in between the above mentioned leaf cells and the power grid to control the flow of the power. The purpose we have described in the previous slide already, why we have a power management unit. And remember here, the power management unit is abbreviated as PMU. Sometimes it is called power management block also. PMU decides and manages the power consumption through segregation known as power domains. How this thing works? It works through the power domains. So here we are done with the power delivery network and we have plunged into the power management unit and we will further plunge down into the power domains in the next slide. Here we will talk about the power domain concept, that is abbreviated as PD. Blocks which can be operated with the same power supply are identified and tied together like this. So here this is power domain 1 which have the power supply VDD1. Numerically VDD1 is different from VDD2 and here it is VDD3. So numerically these things are different, VDD1, VDD2 and VDD3. And operation wise this may be a digital block, this may be an analog block, this may be a macro. So I have colored them with different color. And here is our PMU or PMB, whatever we call it, the power management unit. This forms a power domain. So when they are tied together, this is a power domain PD1, this is PD2 and this is PD3. A particular power domain can be completely kept on or off irrespective of the neighboring block. So this could be on when this is off, right? Or this is on when this is off. So this way any block could be powered up or powered down. A power domain contains collection of design elements that share a primary power and ground supply net. So here you can see here the VDD and VSS will be same for all of the leaf cells here. Similarly here the VDD and VSS will be same for all the leaf cells inside it. Similarly the theory applies here too. The logic hierarchy level where a power domain is created is called the scope of the power domain. The scope of the power domains means this area. So this is the code-wise concept. Generally we code this in UPF. So there the scope thing in terms of the code you will find in the UPF series. There I have explained it with codes and examples and infographics. You can find that in the playlist. Any design element that belong to a power domain are said to be in the extent of that power domain. So these are typical terms you should remember when you are dealing with a power domain. So there is a scope, there is an extent. Okay, what these things are, you should be very much aware with these terminologies. So here we are done with the power domain concept and the power management block, that is PMB or PMU. And here are the power domains. So we have explained with the infographics and the text here how the power domain is there and how they are controlled. So these controls this and this. The power management block PMB or PMU controls all the power domains. Here we will explain the power management unit through infographics. Here is our PMU or PMB. First thing it does kind of operation is the isolation. Here what is performed in the isolation is the clamping of the output pre-sleep. So before sleeping it clamps the output. This is called isolation. Retention. What does it retain? It retains the saved states. Once it is powered up again, it restores from the saved states. So this is the retention operation of the PMU or PMB. Next, it sends another kind of instruction which is called power down. What happens in power down? Shut down and wake up a block. So any block we have told you pictorially in the previous slide. So this is power down and next is reset. What we do in the reset instruction from PMU? any block is in quiet mode pre or after sleep. So reset means that we reset the value, that means in a quiet mode. So these are the typical kind of operation, that means isolation, retention, power down, reset. Those are performed by the PMU or PMB. In addition, to manage the power, the PMU performs another thing, that is it suppresses the clocks during the sleep period. So the long period of inactivity is managed by the suppression of clocks. So these are the things that very technical with the PMU, and here we are done with this particular slide. So let's move on to the next slide. Standard cells for the power management. So in previous slide we have talked about different kind of operation. To enable this kind of operation, what we have to do? We have to use multiple pre-designed standard cells in our chip. What are those standard cells? Switch cell, isolation cell, retention cell, and level shifter cell. So these 4 type of different standard cells are used for power management. These standard cells are designed in coherence with the power management block or power management unit operations, so that whenever such instruction of switching or isolation or retention or level shifting is there, so that time this cell can operate in sync with the power management block. Now we will go in detail one by one of these cells. Power switch standard cell. Here is the picture. Here we have a power gated block and we have a header switch here. So this is a standard cell which is called the power switch cell, and it is placed at VDD, and hence it is called the header switch cell, and it is directly connected to the VSS, and there is no operation here. It is a direct connection, and here there is a switch. It is a header switch, and in case we want to do the operation, switch operation from the VSS, we have to give a footer switch. So this is another standard cell which is a footer switch, and here you can see this is a direct connection with the VDD, and this is the power gated block. These are the block diagrams for the switch cell, that is the power switch cell or the power switch standard cells. Now let us go through some description of it. To turn off power supply to a power domain or a particular time operation, that means for a particular duration, we need power switch to cut the power supply of the VDD or VSS to the domain. That means either we can cut from the VDD or from VSS depending upon how the instruction is coming from the PMU or PMB. Next, the switch cell is created within the scope of the power domain. So we have just shown you 3 power domains in last slide or last to the last slide. There we have talked about the scope. So that means the area of influence of the power domain. Here we have to create the switch. The switch is either turned on or off as per the requirement. So that means it is as per the operation of the clock. It is not as per the whims. It is as per the instruction set that are coming from the sensors or maybe coming from the user. So here we are done with the particular slide. We have explained the switch cells with the header switch and the footer switch for VDD and VSS, and we have gone through the detailed description of it. And let's move on to the next slide. Isolation standard cells. Here the power gated block is there, and we have a isolation cell. Here you can see it's AND gate presentation, and we have a power up signal. So if we have a power up signal and the power gated is there, then only it goes to the always on block. Let us explain with text. When the power gating method is applied in a design in a particular mode of operation, we might end up with few on domains and few off domain. If the outputs of the shutdown domain are connected to the active part of the design, then it might lead to invalid signal transmission and crowbar current. So that means there is a block which is shut off and there is a block which is on. So this is off and this is on, and we have a connection, right? We have to isolate the two, right? This is done by the isolation standard cells. Otherwise, signal going from one block to another block will be misinterpreted with misleading results. To avoid this, isolation cell is placed on the output nets of a switched off domain, interacting with the active portion of the design. And this kind of cell, that means the isolation cell, is also controlled by the power management unit or power management block, that is PMU or PMB. So here we have done a brief description of the isolation standard cells. Let us move to the next slide. Retention standard cells. Sometimes it is called the retention flops also. So here is the schematic diagram of, or you can call it a block diagram. Just start with some of the text. A retention cell is used to retain the data required in shutdown power domain. So that means retain. That means we have to do the save operation. A retention cell consists of flip-flops and save latch as two control signals. One is the save, another one is the restore. When a block is switched off, that means it has been cut off and it is switched off, the states have to be saved, right? So that save instruction is coming from the PMU and that has to be processed by the retention cell, that means this cell. And once the block is powered up again, the restore signal has to come from the PMU or PMB and that has to be processed through the retention cell and that has to act on the power domain. Save signal indicates when the data should be saved in the latch, which is just before the switching of the power. That means save is just when you are just cutting off the power, right? Before that, the save operation has to be performed. Restore signal tells when the data stored in latch, that means this latch, should be restored, which is when the power domain gets back to the active state. The state which is saved in the latch, that has to be restored back into the power domain with the restore signal, and the whole operation is controlled by the PMU or PMB with the help of the specially designed standard cell called the retention cell or retention flop. So here we are done with the description and the operation of the retention cell or flops. So let's move on to the next slide. Level shifted standard cells. Now first we look into some text. When two blocks power operated with different voltage level interact with each other, invalid signal transmission and crowbar current generation may take place. So that means two power domains, one with VDD1 and another one with VDD2. So these are two different VDDs and they are interacting, right? So their level 1, level 0 is different and the forbidden zone is different. So their interaction could be totally goofed up. Prevent this, we have the level shifter cells. To avoid this, the level shifter cells are placed in between the blocks with distinct voltage values. So the level shifter is a kind of cross-domain management or the cross-power domain management cells, specially designed in the standard cell library, which are operated and instructed through the PMU or PMB. Here is the graphical representation or the infographics, right? Let me give some description. Here PD1 operates at VDD equal to 0.8 volt. PD2 is with 1 volt. So low to high level shifter, LH level shifter is working from this to this direction. You can see with the arrow, right? And this is the level shifter cell or this is the level shifter cell. And here is the HL level shifter. That means high to low. High to low means VDD high to the VDD low. So this way the level shifters can be placed in between the communication path of the two power domains. So power domain 1, power domain 2. Now we just switch the high and low value in the next figure here, right? It is PD3 and PD4, right? Here the VDD is 2 volt and here it is 1.2 volt. So this is high and this is low. HL level shifter, that means high to low level shifter, is placed in this direction, and LH, that means low to high, is placed in this direction. In this way, the miscommunication between two different power domains which are talking to each other, two voltages, are done. The level shifter cells can convert high voltage level to low voltage level between power domains. That means cross-domain talk here between the two different power domains are managed by the level shifter. That means the level shifter standard cell works as an interpreter between two different power domains for signal exchanges. Level shifters are placed on signals have sources and sinks. Level shifters are placed on the signals that have sources and sinks operating at different voltages. So this is a typical circuit concept of source and sink, from where to where a signal is going. So you will come across these terminologies when you actually involve in the VLSI design. We are done with the concept of the level shifter cells and let's move on to the next slide. Power management methods. So here we will talk about various power management methods. Before starting that, let me just give you a brief. Whatever we have come across now will be implemented to the power management unit, and here we talk about some methods that typically is done at the very top level to the PMU or PMB. The first thing is the voltage management method. What we do in this, most common of the voltage management method is the dynamic voltage scaling, DVS. Here the circuit can statically or dynamically vary VDD depending upon the throughput requirement. Multi-voltage domain designs can also be classified under this category. So we have talked about multiple VDD domains that is classified under the voltage management method. So these are methods, basically typically methods of managing the power to the PMA or PMB. Throughput management method. Dynamic frequency scaling, DFS, is one of the most used methods in this category. CPU frequency scaling for battery-powered computers is examined in terms of its impact on battery life, system performance, and power consumption. This method ensures efficient use of battery without compromising the system performance. So you can see there are different approaches of saving the power. One is the voltage management method, another is the throughput management method, which is also can be categorized as DFS, that is frequency scaling, right? And next we talk about the functional management method. Here, what we do, we have an alternate design with implementation method that consumes less power to a separate design, maybe from a different FSM. So there we have the less power consumption method in that design. Some of the low power design techniques such as low power FSM design, bus encoding, gate reordering, battery aware dynamic task scheduling represent this kind of cases. So these are very advanced things. As you plunge deep down inside the VLSI design, you will come across all these methods. So I have touched base different methods of power management that are practically done on the portable and wearable devices. Here we are done with the particular slide. Let's move on to the next slide. Hey guys, welcome to the second episode of Unified Power Format. In this episode, we're going to discuss power domain concept. Next, we'll discuss power domain with a single hierarchical instance. The next we'll discuss is power domain instance with child elements. We'll go down further by creating more hierarchy. Then we will explore UPF power domain creation command. Next, we'll go through a detailed example of the UPF power domain creation command. Finally, we'll discuss about UPF power port, power net creation commands. So, if I sum up, in today's episode, we will be both theoretically as well as with examples. We'll show how you can create a power domain with different hierarchy, how you can connect the power ports and the supply nets for all of these power domains. So without any further delay, let's begin. Power domain concept. Here, this picture I have shown you in last episode, but again I am reinstantiating it because there is a necessity. Let me bring my mouse pointer. So if you remember, this is a power management block which controls the entire power distribution of the chip. And here, the different blocks, each with different VDD. And these are termed as different power domains. Now, the matter of fact is that each of these blocks operates its own functionality with the specific VDD they have. So, all internal design elements follow the same VDD as well as the ground each of these blocks. So, let's start the description. Blocks which can be operated with same power supply are identified and tied together. This forms a power domain, as I have shown in the left side picture. A particular power domain can be completely kept on or off, irrespective of the neighboring block. So, the three different blocks in the left hand side, they can operate independently of each other, whether they can stay on or off. A power domain contains a collection of design elements that share a primary power and ground supply net. I already discussed verbally just a few minutes back. The logic hierarchy level where a power domain is created is called scope of the power domain. This scope concept is very much similar to the namespace concept in programming language. So if you are very much familiar with the namespace concept, now you can relate the scope. So here I have not shown any hierarchical design, but in upcoming slides I will show you the hierarchy, because now there could be different hierarchy levels. The top level, 1 level down, 2 level down, 3 level down. So at which level the power domain is created is called the scope of that particular power domain. Next, any design element that belongs to a power domain are said to be in the extent of that power domain. This extent you can also replace theoretically with the word range. That means anything, any design element that comes under a power domain is said to be in the range of that power domain. So here we use the keyword extent. I used another words for your easy understanding, that is range. So two good things you have to learn. One is a scope and another is the extent. So we are done with these slides. Let's move on. So in these slides, we will discuss power domain with single hierarchical instance. Now you can see there are two texts already present in this slide. First and left hand side, that is power specification, and right side it is logic design. Why I have kept? I am explaining that. So this is a particular block which has a supply port marked in red and through which a pink supply net enters into the block. And it is named as A. The same thing has its logic definition, that is our HDL definition, and also it is for the A. So far, we have discussed that we know about the HDL definition. And in this course, you are learning about the left side, which is a power intent definition, which is UPF. Now, in real world, these two blocks are not separated. These two are the same block. In our mind, there are two blocks. From upcoming slides, I will not create two separate pictures, but I will use one picture as is in the real world. So this is the purpose. I want to merge the concept of UPF and your concept of HDL that is in your mind into one single picture. That's why I have kept separated in the first slide, and from upcoming slide, they will be merged. In this case, the only element of the power block is A, which could be a hard macro or a soft IP. That is an instance of a Verilog module, as I have explained. So the purpose of this slide is done. Let's move on. Instance with child elements. Here, we'll see power domains with child elements. So here, let me show the picture with the mouse pointer. So here, this red is a supply port, and through which the supply net is getting connected. And these are sub blocks, or you can say power domains, and which also have a power port of its in color blue. Okay, both the cases. Both are very much look alike with respect to each other. And to put a mirror in between here, you can say this is a mirror image. In terms of topology, I am saying, not in terms of design. In terms of power domain topology. So let me bring on the text now. Here the scope of the power domain is same as the extent. Very much similar, because one is the namespace, that is at which hierarchical level, and another extent or range. So both are same, and both the power domains are neighbors, that is contiguous. Okay. Supply port on A is created using create supply port command. So the red supply port that is at the outer periphery, that is created with the create supply port command. And generally, if it is a top level, right, this will be connected to the ADIO ring in the actual chip. Then supply port is connected to the supply net using the connect supply net command. So this port has to be connected with the supply net. So pink color is the supply net, and that is getting connected with the supply port using the connect supply net command. These are UPF commands. We use create supply net command is applied explicitly for scope A, that is the top level, and implicitly for U1 and U2. So explicit means we are writing it explicitly by words, and implicitly means that we are, by virtue of this command, the U1 and U2 is getting the supply net. So this way explicit and implicit works. Next, supply ports implicitly created on U1 and U2 to connect all the supply nets together. So the blue ports, right, they are implicitly created. I think this picture and the concepts of three different UPF commands, create supply port, create supply net, and connect supply net. These three commands I have discussed here with a pictorial example, and I think it has engraved into your mind. So let's move on to the next slide. Power domain A contains U1/UL. So there is another down level hierarchy, okay? And U2, which do not have another down level hierarchy. So this is the picture. Now you can see here, let me bring on the mouse pointer. So this remains same as the previous picture. Everything here up to here we have seen the change. So there is another hierarchy down there, so which is U1/UL. So these are basically design blocks. And as I have said that these slides, I have merged the concept of the HDL and the power intent, right? So it could be a sub block in the design which requires the power, and this supply net is getting continued through the implicit power ports that is getting created, and it goes up to the U1/UA. Okay. So let's bring up the text now. Here the topology of the logic design is even more complex than the before. Here the power domain consists U1/UA and U2. The two instances in the same power domain which are neither contiguous nor adjacent in the logic design, resulting in non-contiguous power domain. So this is terminology. This contiguous is a terminology. I have explained what it means. And now this kind of topology in power domain is called non-contiguous power domain. These are new concepts, so you have to learn it, and that's why the picture is there for your clear understanding. In this case, when the create supply net command is executed to create a supply net in the power domain, the supply net is explicitly created in A, that is top level, using the name specified in the create supply net command. Supply ports and supply nets are implicitly created in U1, U1/UA and U2. So explicitly created for top level, implicitly created for all the hierarchies further down, okay? And the supply net in U1 connects only to the port on U1 and U1/UA. So this means, let me bring the mouse pointer again. So this supply net is connected here and here. So this is what we are meaning. Although it is clear and evident, but now the picture is with you. But when you are actual design in hand, that time this picture has to exist in your mind and you have to have this text concept along with you to work on. That's why it is explicitly written. Purpose of this slide is over. Let's move on to the next one. Power domain creation command. Now we'll come to the command that we can create a power domain in UPFs. A power domain is created using the command create power domain. The next comes the domain name and next is elements, then list elements means design elements, and the two other are include scope and scope with the instance name. Let's see what are they. The domain name, the new power domain that we are creating. This shall be a very simple name, non-hierarchical, okay? Elements, use this set of design elements in the power domain. Don't worry, we'll see an example, so you will come to know. Include scope. Include scope, we include the scope of the domain in the extent of the power domain. And final, then scope, then the instance name. Create the power domain within this logic hierarchy scope. So the include means we include the existing scope, and here scope means we create our domain within the hierarchy of the scope. So better you understand this with an example. Let's move on. Here, the picture is like that. There is a top. Okay, let me bring my mouse pointer here. Here, this is the top block. Here, we have E1 and PD1. And inside that level, we will create another PD2. That is, this is power domain 1. This is power domain 2. And I also again emphasize that your HDL and your power intent are going hand in hand and in parallel as we have pictorially described. So, let's bring the example. Now, first, create power domain, space PD1. PD1 is the name of the power domain. Then dash elements. Elements is top/U1. Next, we write set scope at this level is /top/U1. So I mentioned that scope means down the hierarchy, at which hierarchy you are defining. You define the scope there, and we are defining with an hierarchical name. Next, we use create power domain PD2. Now, as we create the power domain PD2, it automatically comes under the scope that we have set just the line before. So this is how you can create a hierarchical power domain. Okay. That's all for this particular slide. Let's move on to the next slide. Here, we'll see another example. And let me bring my mouse pointer again. So this is a top block. This is power domain. This is hierarchical power domain, and this is hierarchical power domain, and we can go on like that, but we will restrict ourselves up to this one. So this way we can go. Let me bring up the example. Set scope X. We are setting the scope X, which is at the top level. Create power domain PDX, and we write include scope. That means when we create power domain X, which is the red box and the left figure, we include the already defined scope that we have just defined in the line before. Next, we write create power domain PDY and elements is Y. You can see the picture clearly. And next we write create power domain PDZ, then elements Z. So this way we can create a hierarchical power domain. We have gone through two examples to understand how we do that. And this slide is the extended concept of the previous one. So we are done with this slide. Let's move on. Power ports and power net. Now guys, these are very important thing. When you design a chip with the HDL, it will not operate if it do not have the power ports and the power net. So this is the important part of the UPS that we are going to learn. Power comes from the main power sources to IO pad ring, IA power port, and that get distributed inside the full chip or even down to a block. The supply nets are used to connect power port to power pins for each of the cells. Each cell has its power pin, and the power ports and the power pins are connected to the supply net. Create supply port command. This is basically a command, and the following arguments are port name, domain name, then direction in and out. So a port can carry a power inside or it can come out. So in or out, both the direction can be. The create supply net. We can create the supply net using the net name. Then the next argument is domain, that domain name, reuse and the resolve. I'll discuss detail this resolve one. So first two things, the net name and the domain name is very much clear, easy to understand. And the reuse means that extend the net name as a apply net within the domain name. So why we say this? No new nets are created. Basically, if I exemplify, right, if we have a VDD top, right, and that goes unchanged as a supply net inside sub blocks down the hierarchy, we may not need to change its name if everything will be same as the top level. So that time we can use this reuse. This is done in many of the cases. Next, the resolve one. This resolve is the resolution mechanism which determines the state and the voltage of the supply net from the state and voltage values supplied by each of the individual switches. Default is unresolved. So this resolution means that when a supply net is created, right, how much it is driving. If it is unresolved, that means nothing is properly mentioned. One hot means this supply net is acting like a multiplexer. That means there are multiple outputs. It is supplying one at a time. So it is functioning like a multiplexer. Next is the parallel. Parallel means this supply net there are multiple outputs are connected to this supply net and it is supplying all of them together. That is parallel, which is a very in contrast to the one hot. Okay. So this is the meaning of the resolve switch. So here we have discussed about the power port and the supply net, the supply port and the supply net, the similar meaning. So you're done with these slides. Hey guys, welcome to the third episode of Unified Power Format. In this episode, we are going to discuss UPF and corresponding standard cells. UPF versus standard cells mapping. Header and footer switch cells and corresponding UPF command. Isolation cells and corresponding UPF command. Retention cells and corresponding UPF command. Level shifter cells and corresponding UPF command. Power domain and above mentioned standard cell placement. So, if I sum up today's episode, we are going to correlate the 4 special type of UPF command and their corresponding 4 special type of standard cells. We'll go thoroughly in detail and in each of them. So, let's begin. UPF and standard cells. So here we will talk about 4 type of UPF commands and the standard cell. Majorly these are switch cell, isolation cell, retention cell, and level shifter cell. So in standard cell package, these 4 type of cells are there and these are special type of cells. And in UPF, we have the exact same commands to apply these kind of cells in the actual design. In upcoming slides, we will discuss about all of these cells as well as the corresponding UPF command. So here we have, let me bring my mouse pointer. The UPF command is create power switch. Okay. Corresponding cells are header or footer switch cells. These are picked up from your standard cell library. Now, again, the next command is set isolation. This command picks up isolation cells from your standard cell library. These commands are used in your UPF deck and these are coming into your actual design to implement these commands. So next command is set retention. It calls the retention cells or also known as retention flops from your standard cell distribution. The next command is set level shifter. This calls level shifter cells from the standard cell package. Now, if I sum up, all these 4 commands picks up one particular type of special standard cells from your standard cell design kit. And these are very, very important. So we will explore one by one each of them. And concurrently, we will correlate the command and the switch, the physical standard cell. So let's move on to the next slide. Power switch cell. So here you can see the header switch. Header means it is connected with the VDD. These can cut or join the power to a power gated block. And here VSS is continuous. There is no switch in between. The next type of switch could be a footer switch, which we connect in between VSS and the power gated block, whereas the VDD is connected directly. Now, here you can see based on the position of the switch cell, we call it either a header switch or a footer switch. To turn off power supply to a power domain for a particular time of operation, we need power switch to cut the power supply, that is VDD or VSS, to the power domain. So this is the purpose we have our power switch cells. The create power switch command in UPF defines an instance of the power switch in the power domain. The switch is created within the scope of the power domain. The switch is either turned on or turned off as per the requirement. So guys, if I sum up, either it is a header switch or it's a footer switch. In both cases, it can truncate the power to the power gated block. And the corresponding UPF command is create power switch. We are done with these slides. Let's move on to the next slide. Isolation cells. So here, let me bring my mouse pointer. Here we have a power gated block, which we are connected with a always on block. And in between we place the isolation cell, and we keep our control in hand whether to isolate or to connect these two blocks. So this cell is called isolation cell. Now let me bring up the text. When power gating method is applied to a design in a particular mode of operation, we might end up with few on domains and a few off domains. If the outputs of the shutdown domain are connected to the active part of the design, then it might lead to invalid signal transmission and crowbar current as a result. This is very evident. If one block is off, another block is on, and one signal is traversing in between, so it will send or receive erroneous signals. This is very, very evident and clear. To avoid this situation, an isolation cell is placed on the output nets of the switched off domains interacting with the active portion of the design. This is what I have just shown in the above picture, in this same page. So we are done with the both pictorial and text explanation. Let's move on to the next slide. Here we talk about the isolation UPF command. The set isolation command specifies the design elements in the domain to isolate using the specified strategy. Isolation supply nets can supply a single power net, a single ground net, or both. So, one particular UPF command, it can either specify a power net or a ground net as an isolation net. If only an isolation power net is specified, then automatically the primary ground net serves as the isolation ground net. So one complements the other. If one is specified, other is automatically selected. Next, if only an isolation ground net is specified, then primary power net serves as the isolation power. So in case we specify the ground net as isolation ground net, then the primary power net is automatically treated as the isolation power net. That's the beauty of the UPF command. So at least one of the isolation power net or isolation ground net switch has to be specified unless there is no isolation specified. So when we are writing this command in our UPF text, we have to specify one of these two switches. So this is what we have to keep in mind. Now we're done with this particular slide. So let's move on. Retention cells and flops. So here let me bring my mouse pointer. This is a structure of a retention cell. And here the most two important signals is save and restore. So this entire setup does what? It stores the last state. If a save signal is sent, it will store the last signal inside it. And before switching off this power block. Once the power comes back to this block, the restore signal is activated. The last save state is retrieved. So this is the purpose of the retention cell. A retention cell is used to retain the data required in shutdown power domain. A retention cell consists of a flip-flop and a save latch and has two control signals, that is save and restore. Save signal indicates when the data should be saved in the latch, which is just before switching off the power. The restore signal tells us when the data stored in the latch should be restored, which is when the domain gets back to the active state. So this is the theoretical explanation behind the retention cell or retention flop, whatever name it is called. So we are done with this slide. Let's move on. The retention UPF commands. The set retention command specifies which registers in the power domain needs to be retention registers. Only the registers implied in the elements list shall be provided retention capabilities. At least one of the retention power net or retention ground net shall be specified. If only retention power net is specified, the primary ground net shall be used as the retention ground supply. And if only retention ground net is specified, the primary power net shall be used as the retention power supply. If both are specified, then these options specify the supply net to use as a retention power and ground nets. So guys, it is very much simple that this particular command has to specify along with any one of the retention power net or retention ground net. Okay, so this will instantiate the retention cells or flops into your design through the UPF tech. We are done with this particular slide. Let's move on. Level shifter cells. So here, let me bring my mouse pointer. Here is the picture. Here is power domain 1, here is power domain 2, here VDD is 0.8 and here is 1. So if a signal travels from this PD to this PD, what happens that here VDD is low and here VDD is high. So the logical 1, 0 will be different. Okay. So we need to normalize these voltage mismatches, and that's why we introduce the level shifter cells. So here we can see if the signal traverses from a low VDD to high VDD, we use a.k.a. level shifter, that is low to high level shifter. And if the voltage or the signal traverses from a high VDD to a low VDD one, we use the HL level shifter, that is high to low level shifter. Similar way, there is another PD here, another PD here. Here the left side one is a higher voltage and the right one is at lower voltage. So from this domain to this domain, what happens that we use HL level shifter, high to low. And from here to here we use LH level shifter. So this way we apply our level shifter cells. When two blocks powered with different voltage levels interact with each other, invalid signal transmission and crowbar current generation may take place. So that is what we just
discussed. And to avoid this, level shifter cells are placed between the blocks with distinct voltage values. Now, this distinct voltage values means it could not be random. For this particular level shifter, the to and fro VDD must be clearly defined. Okay, and that's why we have in the StdCell library, we have these specific L2H and H2L level shifter cells specifically designed. Level shifter cell can convert a high voltage level to a low voltage level between the two domains. Level shifters are placed on signals that have sources and sinks operating at different voltages. So here, as we go from PD1 to PD2 or PD3 to PD4 or vice versa, one acts as a source, another acts as a sink. So here we have corresponding level shifters. So we're done with this slide. Let's move on. Level shifter UPF command. The set level shifter command can be used to set a strategy for level shifting during implementation. Level shifter rule can be low to high, high to low, or both. If low to high is specified, signal going from a lower voltage to a higher voltage gets a level shifter when the voltage difference exceeds that specified by the threshold. If a high to low is specified, signals going from a higher voltage to a lower voltage gets a level shifter when the voltage difference exceeds that specified by the threshold. If both are specified, it is equivalent to having specified both rule strategy. In summary, this is the particular UPF command that pulls in the particular types of level shifter from the StdCell library. We're done with these slides. Types of level shifter cells. So here we'll discuss different types of level shifter cells. Level shifter position defines whether the level shifter cells are placed in the logic hierarchy. All necessary supplies need to be available in the specified location. Self. The level shifter cell is placed inside the model or cell being shifted. Parent. The level shifter cell is placed on the parent cell or model being shifted. So you can see that this type of level shifting classification is done based on the design topology on which we are placing our level shifter cell. The next topology is sibling. A new sibling is created into which the level shifter cells are placed. So we covered self, parent and sibling. The next one is fan out. A level shifter occurs at all fan out locations, that is sinks, of the port being shifted. Automatic. So for automatic, the implementation tool is free to choose appropriate locations. So guys, we're done with this particular slide. Let's move on. StdCell placement. Let me bring my mouse pointer. Here you can see this picture I have shown you in last episode. Power domain X, power domain Y, power domain Z, and inside again if we go down we have Y1 and Y2. Here we have Z1 and Z2. So this is PDX, this is PDY and PDZ, and here is our boundary. This is just as our regular PF structure we get this, and now if I bring on the special cells where they will be placed. So the isolation cell can be placed inside the two interacting power domains, that is here. And the level shifter cell also can be placed here. They can be placed here also if these two are interacting. So based on which domains are interacting, we can place our special cells at these locations. So this is a very simple explanation, and the picture is now clear to you where these cells are placed. With that, we are done with the slide. Hey guys, welcome back to the computer screen, and in today's episode we are going to discuss the below points. First, we'll do our introduction Next, we will talk about the conventional level shifter operation. Next, we will talk about level shifter StdCells. We will proceed our discussion by talking about positioning of level shifter cells in the VLSI chip. Next, we will talk about various level shifter variants. Finally, we will summarize our entire discussion. So we are done with this particular slide. Let's move on to the next slide. Introduction. In modern ASIC SoC design, different design blocks like digital, analog, macros are fabricated on a single chip and needed different supply voltages for optimum performance, efficiency and speed. In the right hand side picture, you can see there is a power management block. Here, this manages the entire power of the chip, and here we have a digital block, analog block, macro. This operates at VDD1, this operates at VDD2, and this operates at VDD3. In multi-voltage domain, also known as power domain system, the logic gates on non-critical paths are operated with low VDD, also known as StdCell, and gates on critical path are operated with high VDD, also known as VDDH. Chip with different supply voltage domains use level shifters to convert and propagate logic signals among different power domains. So in the right hand side picture, you can see already there are several power domains. So if these power domains have to communicate among them, they might have to use the level shifters for the conversion of the logic levels. When a logic 1 signal of VDDL block drives a VDDH logic gates block, the PMOS of VDDH operating logic gate blocks may not become perfectly on, rather may lie partially on and weakly on states. So this might be a scenario if we do not use the logic level shifters. The level shifters are inserted at proper domain crossings to change the voltage levels accordingly to mitigate the above situation. That means somewhere it is partially on or weakly on. So that should not happen. That is protected by inserting level shifter. Also, level shifters are inserted between core circuits and I/O circuits in the multi-power domain chip. Core means, so in this picture, you can see this is the core where all the blocks are there. Obviously, around there will be I/O circuits for connecting with the outer world. So all those I/O circuits, when they are communicating here with these core blocks, right, level shifters are also needed at those junctions. We are done with this particular slide. Let's move on to the next slide. Conventional level shifter operation. So folks, before proceeding any further step, in this slide we will demonstrate a basic level shifter, how it operates. That means how it changes a voltage level from VDDL to VDDH. On the left hand side we will be going through the text, and right hand side we will be going through the corresponding circuit diagram. The circuit diagram is a conventional level shifter that converts the logic level 1 from VDDL to VDDH. Right hand side you can see the logic circuit here. Now let me start the text, and the labels I will do dynamically while we are discussing. Just before proceeding anything, you can see there is only PMOS and NMOS in this circuit, and there is one input port and output port. You can see the grounds with the green triangles and the VDDs with the red rectangles supplies. Okay, so let me go through the description and label accordingly. This is VDDL, this is VDDH, this is VDDH, and this is VDDL. So we have marked the supplies where the VDDL is given and where the VDDH is given. Now let us proceed about the signal propagation to this level shifter. When one, that is VDDL, is applied to the input, here is the input, P5 goes off and N5 turns on, resulting output 0. So this is P5, N5 and out. This 0 at node T5 is applied to N1 and turns it off. Here is corresponding P1 and T1. It also goes to the inverter T4, which makes T4 on and N4 off. So here is T4 and P4 and N4. The output of T4 is now 1 and is applied to N2, thus turning it on. This is N2, P2 and P2. N2 now pulls P2 to 0. This turns on P1, in turn pulls P1 to 1. P1 is connected to the gate of P2, which now gets turned off. T2 remains at level 0, which turns on P3, and this is N3.
P3 pulls up the value of out to logic 1, that is VDD H, in the output port. So this way, the level shifting operation happens inside a basic level shifter cell. So here we have gone through the operation of a conventional level shifter circuit, and we will move to the next slide. Level shifter standard cells. When two blocks are powered with different voltage levels interact with each other, invalid signal transmission and crowbar current generation may take place. And here is our picture where we have different power domains, and we can see here, let me bring my mouse, here LH level shifter, it is HL level shifter. So how this abbreviation comes? Here you can see VDD is 0.8, here is 1. So LH means low to high. So here if the signal goes in this direction, the conversion will be low to high. That means this is low, this is high. When we are comparing two VDDs, this is a low VDD, VDD-L, this is VDD-H. And when we are going this direction, so we are giving HL level shifter. However, if this scenario is different here, the power domain here, if it is 2 volt and here it is power domain 4 is 1.2 volt. When the signal goes from here to here, we use, so this is VDD-H and this is VDD-L now. So here we insert a HL level shifter, and if the signal is going from this to this direction, we are using a LH level shifter here. So I think it's a very straightforward description of how the level shifting operation is happening between VDD-L and VDD-H for various power domains inside a single chip. The right hand side picture is of a single chip where we have PD1, PD2, PD3 and PD4, the 4 power domain with different VDDs. Let's move on to the next point. To avoid this, level shifters are placed between the blocks with distinct voltage values, as we have seen in the picture. Level shifter cells can convert high voltage levels to low voltage level between the domains. And level shifters are placed on signals that have sources and sink operation of different voltages. Now, as you can see in the right hand side picture, right here PD1, PD2, here when the signal is moving from one direction to another direction, this acts as a source and this acts as a sink. And when we are doing the reverse, say the signal is transmitting from PD2 to PD1, here this acts as a source and this acts as a sink. In actual VLSI design, these level shifters may be not here, may be placed at this boundary or this boundary, or maybe here. So that is vary from one PDK to another PDK, where you will find different positioning of the level shifters here or here. We are done with this particular slide and the description with the right hand side infographics. Let's move on to the next. Positioning of the level shifter cell. This is very important slide. You must emphasize each and every point in this slide. Level shifter position defines where the level shifter cells are placed in logic hierarchy. All necessary supplies need to be available in the specified location. Here you can see the entire domain here. The top domain is here. Here is PDX, power domain X, power domain Y, power domain Z. Here we have isolation cell. In previous episode we have talked about this. And here in this episode we are talking about level shifter. So here signal is crossing from X to Z. It is having a level shifter. And inside the PDZ we have sub block Z1, Z2. But in that case we are not using any level. Even for PDY we are having Y1, Y2 different blocks. For there we are not using level shifter. We are using level shifter at the boundary only. That means with PDX versus PDY, entire supply voltage is different. PDX, the VDD is different, and PDZ, the VDD is different. Similarly, PDY, the VDD is different from PDZ and PDX. The VDD supply for X, Y and Z domain are different from each other. Self, the level shifter is placed inside the model or cell being shifted. This is what I have just touched based in previous slide, that the level shifter can be there inside a cell being shifted, right? So self is a position. Parent, the level shifter is placed in the parent cell or model being shifted. So here if you can see, right, PDX is a kind of parent here. You see if the top is PDX, right? Sibling, a new sibling is created into which the level shifters are placed. So here Y and Z are siblings, right? So here you can see we can place the level shifter inside these siblings. Design architecture have to be like that. Level shifter cells either have to be placed in the parent or sibling or cells in this kind of manner as per the voltage designs and internal circuits. And these things may vary from one PDK to another PDK. Fan out. Level shifter occurs at all fan out location things of the ports being shifted. automatic. The implementation tool is free to choose the appropriate location. So these are various types of level shifter cells which comes pre-designed in the StdCell library, and they can be used by the router tool or the PNR tool, that is the place and route tool, based on the type of the level shifting description. So if it is self, it will be placed inside the cell. Parent, it goes to the parent power domain. Sibling, it goes in the sibling, that means the internal power domain created. Fan out is a position, and automatic, it is free to use anywhere. So these are position based level shifter cells available in a StdCell library. We're done with this particular slide, so let's move on to the next slide. Level shifter variants. In this slide, we will talk about variants. In last slide, we talked about positioning, and in this slide, we will talk about variants. Unidirectional. All input pins are dedicated to one voltage domain. All output pins are dedicated to another. So here we are talking about the input and output of the level shifter pins. Bidirectional with dedicated ports. Each voltage domain has both input and output pins, but the data direction of a pin does not change. Bidirectional with external direction indicator. When an external signal is changed, input becomes output and vice versa. Bidirectional with auto sensing. Pair of I/O spanning voltage domain can act as either input or output depending on external stimulus without need for a dedicated direction of the control pin. So you have the definitions talked about in this slide, and in the previous slide you have some other positioning information. Where you will find all this information? When you receive the documentation of a design kit.pdk, that is DK or PDK from the vendor, you will get a documentation, text documentation with the graphical representation and data sheet. So there you will find all these details of what type of level shifters are there, how you can use them, and what are the categories. So these two slides will help you in that part when you are actually designing in VLSI. We are done with this particular slide, so let's move on to the next slide. Summary. Let us summarize so far what we have discussed. A level shifter, also known as voltage level translator or logic level shifter in digital electronics, is a circuit used to translate signal from one logic level or voltage domain to another. It allows compatibility between different subchip blocks of ICs with different voltage requirements, such as TTL and CMOS. Modern systems use level shifters to bridge domains between processor, logic, sensors, and other circuitries. In VLSI, most common logic levels have been 1.8 volt, 3.3 volt, and 5 volt. There could be other variations. You must not have only these values in your mind, so be open-minded at this point. However, levels above and below of this voltage are also used, which I have just mentioned. A level shifter increases the total area of the circuit, which in turn increases the power dissipation. So this is a drawback of the level shifter being used inside a chip. If voltage levels are far apart, the level shifter design becomes complex and error prone. So this is another risk if and only if the voltage levels are very far apart. Otherwise, it is very fine and good to go. Generally, it's a theoretical point. However, these points are well taken care when the power performance and area, that is PPA, is done on any StdCell library. So you don't have to worry when you are using a already characterized StdCell library that you are receiving from your StdCell vendor. We are done with this particular slide. Hey guys, welcome back to the computer screen, and in today's episode we are going to discuss about the below point topics. First, we will go through the level shifter philosophy. Next, we will briefly explain the clock domain crossings. Next, we will briefly explain the voltage domain crossings. Next, we will start our discussion on advanced level shifters by talking about cross-coupled level shifter. Next, we will talk about the bootstrap level shifter. Next, we will talk about DCVS basic level shifter. And in the next point, we will cover the DCVS advanced level shifter. Finally, we will summarize our entire discussion. We are done with this particular slide, so without any further delay, let's begin. Level shifter philosophy. Among multiple voltage domains, threshold voltages are also different. One thing I would like to say here, in StdCell distribution, you will find LVT, HVT, UHVT, and many type of VT, that is threshold voltage variations.
In order to interface between the super threshold, near threshold and sub threshold cells, appropriate level shifters must be placed. So this kind of threshold boundaries based on the different VT dependency of the standard cells being used from all the distributions like LVT, HVT, UHVT, etc. Here goes our level shifter diagram. This is the sub-threshold logic circuit and this is the super-threshold logic circuit, and in between we have our level shifter. In between you can see that 0.4 volt and 1.12 volt, these voltages with reference to which the signal propagates is also marked in the diagram. The level shifter is required because the logic high output of the sub-threshold gate does not meet the minimum logic high input of the super-threshold gate. The three combinations that are required for hybrid methodology include interfacing of sub-threshold to super-threshold, sub-threshold to near threshold, and near threshold to super threshold. So when in a circuit we have multiple VTs, we will see multiple combination of the last three bullets that we have just discussed. We are done with this particular slide, so let's move on to the next slide. Clock domain crossings. Each clock domain or voltage island can be considered as individual layer block. In a modern day chip, that is in a SoC, we can find multiple clock domains or we can find multiple voltage domains as we have just mentioned earlier. Here is a simple diagram with multiple flip-flops and muxes where this is the first clock domain owned by clock A and this is the second clock domain owned by clock B. So this way, different clock domains are there in a modern day SoC and these clock domains evidently cross at some point. Number of clock or voltage domain crossings need to be minimized. Among multiple clock domains, all the scan cells of same clock domain are tied together. Scan cells, you can relate the cells, those are used for the DFT, that is designed for testability. All flops in the same clock domain are also grouped together. The number of interclock domain lockup latches are kept fixed. So we are done discussing about the clock domain crossings. Let's move on to the next slide. Voltage domain crossings. In multiple voltage island or blocks, logic level shifter is needed to calibrate the voltage change between different voltage of logic levels. Here is a brief and neat diagram of multiple voltage domain, or we can call multiple power domain, managed by a power management block of a modern day SoC. Here, the power management block controls the power distribution among PD1, PD2 and PD3. And if any signal is traversing among the three, that is PD1, PD2 and PD3, those signals have to be taken care and go through by the desired voltage level shifters. Scan chain design in DFT for multiple voltage island also raises the power sequencing issue. One solution is that power sequencing circuitry is held to the power on state during the test operation. Another solution is that each power sequenced island is tested independently. The combination of multiple clock domains or multiple voltage domain islands needs special consideration and attention. We are done talking on voltage domain crossings. So let's move on to the next slide. Cross-coupled level shifter. So far, we have discussed the different theoretical backgrounds and physical needs of a chip of having a level shifter to the clock domain crossings or voltage domain crossings. Now, in this slide, we will talk about the cross-coupled level shifter, which is an advanced level shifter in modern day IC technology. Conventional level shifters are designed using cross-coupled P MOSFETs. So here is a circuit diagram of a cross-coupled level shifter. The circuit diagram is very easy to understand. There are two sets of CMOS here on the right-hand side column and the left-hand side column. And you can see the connections very neat in this diagram. So let's proceed on the description. The incoming low voltage signal is inverted using an inverter connected to a low voltage domain, that is VDDL. Cross-coupled P MOSFET transistors P1 and P2 are used to pull out to the high voltage, that is VDDH. So in this diagram you can see clearly the VDDH and VDDL, that is the high VDD and low VDD are mentioned clearly. We are done talking on cross-coupled level shifter. Let's move on to the next slide. Bootstrap level shifter. So let's explore this new kind of advanced level shifter.
In bootstrapping technique, transient power is reduced during the level shifting. Let us see how in this diagram. This is also a very neat diagram, and you can clearly see every active or passive devices in this circuit and their interconnections. Two boot capacitors C boot 1 and C boot 2 replace NMOS transistor to maintain the voltage difference at the gate terminals of P2 and N2. The pull-down network NMOS N2 at the output stage is driven by 0 and VDD-L, whereas the pull-up PMOS is driven between the difference of VDD-H and VDD-L and the VDD-H itself. Bootstrapping technique achieves lower power at the expense of significant increase in physical area due to the relatively large boot capacitors. We're done talking about the bootstrap level shifter here in this slide with a neat diagram. So let's move on to the next slide. DCVS basic level shifter. One of the famous level shifter design approach is based on differential cascade voltage switch, abbreviated as DCVS level shifter. Here is a neat diagram of our DCVS basic level shifter. The input NMOS transistor are controlled by a low voltage input signals. This low voltage is shifted to a high voltage at the output of the level shifter. The DCVS level shifter operates as follows. In the beginning, in equal to 1 and in bar is equal to 0, out is equal to 1 and out bar is equal to 0. Then the transition happens as in equal to 0 and in bar is equal to 1. The NR goes off and NL goes on. PMOS PL remains at 0 voltage, maintaining PL on to resist the NL transistor by simultaneously charging node out. NR and NL is connected to the low input signal related to VDD-L and operate in cutoff region. Gates of PR and PL are connected to high voltage supply. NL and NR struggle to sink more current than the PMOS pull-up transistor source. If NL sinks greater current than PMOS pull-up transistor source, node out discharges. PR transistor toggles from off state to on state and charges node out. This cuts off pull-up transistor PL, completing the transition. So we are done talking about the DCVS basic level shifter. Let's move on to the next slide. DCVS advanced level shifter. Here, additional logic NRT, NLT, PRT and PLT is added over the basic structure for improved performance, as you can see from the right hand side picture, which is a clean and neat diagram of the advanced DCVS level shifter. NMOS, NLT and NRT are biased at a nominal voltage VDD-H. Therefore, NR and NL size can be smaller than a standard level shifter. However, NL and NR should be sufficiently large to force the transition within differential structure. When the differential input is sufficiently shifted, the significantly stronger NLT and NRT transistors complete the transition. PMOS, PLT and PRT are controlled with the corresponding input voltage to limit the current flowing through the full voltage pull-up transistor PL or PR. PMOS, PLT and PRT are controlled with the corresponding input voltage to limit the current flowing through the full voltage pull-up transistor PL or PR. For high input in or in bar, PLT or PRT is fully on, providing the desired charging current. PRT or PLT limits the current, allowing the NMOS pull-down network NR or NL and NRT and NLT to discharge the out and out bar node. So we are done talking about the DCVS advanced level shifter. Let's move on to the next slide. Summary. Let us summarize our entire discussion. A level shifter, also known as voltage level translator or logic level shifter in digital electronics, is a circuit used to translate signals from one logic level or voltage domain to another. It allows compatibility between different subchip blocks of IC with different voltage requirements such as TTL and CMOS. In VLSI, most common logic levels have been 1.8, 3.3 and 5 volt. However, levels above and below these voltages are also used. Advanced level shifters such as cross-coupled LS, bootstrap LS, and DCVS LS, etc. are used as modern-day level shifters. Here in this line, LS means level shifter. So, we are done with the summary.
Hey guys, welcome back to the computer screen, and in today's episode we are going to discuss the below points. Power management methods. Next, we will introduce the retention concept. Then, we will explicitly discuss about the retention cell, also known as TLATS or retention flow. Then, we will cover the topics PSO and SRPG. We will later go in the nomenclature abbreviation detail. Next, we will talk about the simulation and verification stage for the retention cell. Next, we will talk about the physical design stage for the retention cell. Next, we will talk about two types of retention cell, that is balloon type and master-slave type. Finally, we will summarize everything that we have discussed. That's the menu for today. Without any further delay, let's begin. Power management methods. Here in this slide, we will show you infographics through which you will be aware of different power management methods that are used in modern day chip making. Here goes our power management, and the different method starts here. First, in chip design, we can use multiple threshold voltages, and this threshold voltage variation comes in the standard cell nomenclature like UHV, HVT. All those nomenclatures nowadays you will find inside any standard cell package. Multiple VDDs. Because of the various power domains, you will get multiple VDD variation of standard cells. Power gating is a technique by which also we do the clock gating for the power management. Next, another important way of power management is dynamic voltage scaling. We have another similar scaling called the dynamic frequency scaling, which is used for power management. Next, we have retention block or cell that we use in design. We use the isolation cell also for the power management purpose. We do use a power switch cell in the power management. For various VDD domains, for exchange of signals, we use the layer cell. So it also comes under the power management. So these are the various methods that we use for power management of a chip, especially in a chip where we have a PMU, that is a power management unit. We will see many of these methods present there in a modern day IC. So we are done with this particular slide. Let's move on to the next slide. Introduction to the retention concept. When a device or circuit is inactive for a long period of time, a snooze button helps save the battery. Nowadays we use mostly handheld devices, right? And inside that, saving the battery is a very important factor, because once we charge a handheld device, we will expect it to run for a longer time. Memories or registers are not capable of keeping their information while the device is off. When a particular power domain inside a chip switched off, it is bound to lose its memory. The obvious consequence that we experience in modern day power domains. And here is a photograph for the various power domains. You can see here, this is the power management block, and here it is the power domain 1 with the V1, power domain 2 with VDD2, and power domain 3 with VDD3. So this block diagram, you can see we have three different power domains, PD1, PD2, and PD3, which is controlled by the power management block. So once the chip is in operation, say PD2 is not being used, so the power management block will send an instruction to switch off for its inactive period, and in this situation is going to lose its memory. Now this is a challenging situation, and how we tackle it, we are coming to that point. To save such scenarios, special retention cells have been adopted in most of the commercial standard cell libraries coming from the foundries like TSMC, UMC, GF, etc. to support the state retention power gating, also abbreviated SRP. Retention cells store the last state before power off of a clock inside the power domain. So from the right hand side picture, it is clear to you, if we can switch off one particular power domain, that the last states will be saved in the retention cells. Thus, it allows the system to continue its operation from the last known state and faster wake up of a block, because this is a step mostly found in the handheld devices where one particular power domain is switched off while it is inactive, and once it wakes up from that state, it can pick up values from the last known state very fast from the retention cells, and this way the device can operate very fast.
The only drawback is the retention mode consumes a little more current than the powered off mode. So we have gone through the introduction here and we are done with this particular slide. So let's move on to the slide. Retention cell or P-latch or retention flops. These are the different names of the same thing, and here in this slide we are going to talk about this. Retention cell has a flip-flop and a state-saving latch. Here is the block diagram of a retention cell. You can see as we described dynamically. Supply of the flip-flop is switchable and the latch is always on. The latch associated with it will retain the prior state when it is powered off. The multiplexer allows us to save and restore the logic in latch. A retention cell consists of a flip-flop and a save latch and has two control signals, save and restore. The save signal indicates when the data should be saved in the latch, which is just before switching off the power of the particular power domain. Restore signal tells when the data stored in the latch should be restored, which is when the domain gets back to the active state. PSO and SRPG. Under power gating comes the power shutoff, that is PSO, where unutilized blocks are switched off completely to stop any leakage current. PSO is triggered for any block whenever it goes to standby mode. It should be verified along with the working RTL, ensuring that the entire chip operates flawlessly whenever any such powered off block is turned on again. State retention power gating SRPG. To implement PSO, state retention cells are bare necessary to store existing state of the blocks before it shuts down. During synthesis, isolation cell, retention cell, level shifter cell and always on cells are inserted automatically based on the CPF or UPF description. So we are done with the power shutoff, that is PSO, and state retention power gating, that is SRPG in this slide. So let's move on to the next slide. Simulation and verification stage. Here in this slide, we will talk about placing of the retention cell to the simulation and verifications, because throughout the design, the presence of the retention cell has to be properly implemented through thorough checkup. So here we go. When the verification environment launches test cases during simulation, different power states are entered. The modules in the supply network propagate their state throughout the network. It generates the power management signals such as enable the power switches and of the isolation cell. Save the state in retention cell, that is, store the register values before they are shutting off. Restore from the state retention cells to retrieve register values once the power domain is switched back on. This information is coded during the CPF or UPF file creation. Monitors inside each module such as power switches, isolation and retention record and log the sequence of events during the front-end simulation. After simulation, the logged events are automatically evaluated and checked. Any activity found inside a deactivated domain is immediately reported. This way, in the front-end part, retention cells are properly and thoroughly placed and checked. We are done with this particular slide, so let's move on to the next slide. Physical design stage. Here in this slide, we will talk about the implementation of the retention cell in the physical design part of the chip design. While the system is created, power design is coded in UPF or CPF. Power switches to change domain supply states are created. Power domains are described and connected to the supply network. After the floor plan completion, all its specifications are dumped onto a design exchange format, that is def file. The inputs to the placement tool are the gate level netlist, floor plan def file, power intent file, timing module files and reference library files. Sanity checks are performed on the floor plan file and gate level netlist. The power intent file is checked and any violation between the floor plan data, gate level netlist and power intent are corrected at this stage. The floor plan information is then loaded onto the backend tool.
Next, the power intent is omitted, which adds isolation cell, retention cells, and enable level shifter and power multiplexer. And the backend versions, that is the layout version of these cells, are picked up from the standard cell library. So that was all about the implementation of the retention cell in the physical design stage. So done here. Let's move on to the next slide. Types of retention cell latch. The retention cell can be of two types. The first one is a balloon latch and second one known as a master-slave latch. In the upcoming slides, we will get familiar with these two types of retention cells. So done with this particular slide, let's move on to the next. Balloon type retention cell. In a balloon type retention register, the retained value is held in a shadow or additional latch, often called the balloon latch and usually powered by the cache retention supply. This retention supply keyword is from the CPF or the A balloon type retention register typically has additional controls to transfer data from a storage element into the balloon latch, also known as the save stage. And the transfer data from the balloon latch to the storage element, also called the restore page. The ports to control the save and restore pins of the balloon style retention register needs to be available in the design, describe and implement this type of retention register. The balloon element is not in the functional data path of the register. That was all about the balloon type retention cell, and we are done with this particular slide. So let's move on. Master-slave type retention. Let us see what is a master-slave type. A master or a slave alive retention register. The retained value is held in the master-slave latch and also powered by the retention. This is a keyword from the CPF or UPF. In this case, the retention element is in the functional data path of the register. This is a very much striking difference with the previous slide. Remember this. A master or a slave alive type retention register typically does not have additional save or restore controls, as the storage element is the same as the retention element. Additional controls on the register may part the register into a quiescent state and protect some of the internal circuitry during the power down state, and thus retention state is maintained. The restore in such registers typically happen upon power up, again owing to the storage element being the same as the retention element. Thus, this style of registers may not specify save and or restore signals, but may specify a retention condition that could take the register in and out of a retention state. So, this was all about the master-slave type retentions. We are done with this particular slide, so let's move on. Summary. Retention cell is an integral part of the present standard cell library and used in the ASIC design today. It is a must for the chips where there are multiple power domains are existing. In the power-aware RTL design, retention cell is equipped to the UPF or CPF description. There are two major types of retention cell known as balloon type and master-slave type. So we have summarized our entire discussion here. We are done with this particular slide. Hey guys, welcome back to the computer screen, and in this episode we are going to discuss about the below points. Various power management methods. Problem scenario among power domains. Isolation cell to the rescue. Isolation method and isolation cells. Isolation standard cell example. Drawbacks and improvements. And finally, we will summarize our entire discussion. So that's the menu for today. Without any further delay, let's begin. Power management methods. In modern day ICs, the power management inside a chip is done through several different ways, and here in this slide we are depicting all of them. The first one of the power management method is to use multiple threshold voltages, that is multiple VTs. And we use multiple VDDs for multiple power domains inside a single chip. We use power gating method for managing the power to different blocks inside a same chip through PMU or power management unit. Also, we use clock gating for the clock cells. We also use dynamic voltage scaling. In addition, we use dynamic frequency scaling too.
From the standard cell families, we use the retention block or cell and isolation cell and power switch cell and level shifter cell. So these are 4 special standard cells that we use for power management. So here the entire picture is clear to you now. So let's move on to the next slide. Problem scenario among power domains. Inter-domain signals can become complicated if the connecting interface changes during different power modes. Here is a very short and sweet example of multiple power domains. This one is a power domain 1, that is PD1 with VDD1. Here it is depicted as a digital block. Here it is PD2 with VDD2 and it's an analog block. PD3 with VDD3 for macro. And here is our power management unit, that is power management block that manages the power among all these independent power domains. So power domain 1 is independent of 2 and 2 is independent of 3, and mutually they are independent of each other. These blocks may communicate among them during the normal course operation of the entire chip, and these signals become complicated when the chip is in action. Let us see what happens. During power getting operation, the circuit will contain few on domains and few off domains together at any point of time. So here in this particular picture, you can see, right, this block is on, the digital block is on, and the macro block is off, and the analog block is on. So at some point these two are on, this is off. As I have said that these blocks are interconnected, what can happen? Let us see. In such situation, output of an off domain sends an invalid signal to the on domain. And this is a scenario what happens. So this is a power gated block. So imagine any of these blocks as this block, which is a power gated block, and another one is the active block. So this is the signal transmission line here, and here we see there is no isolation. And if there is no isolation, the line, if it is off, right, then this line, the signal line, will contain floating output. So it could be 1, it could be 0, could be in between. So no one knows what is there. It is in a metastable state. So the active blocks receives an invalid signal here. When this floating voltage is propagated to the inputs of the receiving end, a short circuit current is produced. Crowbar current may flow because output pins the off domain might be in the metastable state or dangling. So this is another risk. There can be a crowbar current, and that can confuse the active block of about the signal that is coming from the power gated block, which is off at particular time, and that time the active block may get confused about the coming signal. So the scenario is well explained with the infographics and text. So let's move on to the next slide. Isolation cell to the rescue. So this situation which we have just explained, how to overcome that situation. Here in this slide we will discuss about that. To deal with such problematic situations, specially designed standard cell, also known as isolation cell, is placed in between power gated block and the active block. So here is our problematic situation. You can see the power gated block and our signal line is carrying a floating value, and here is our active block. There is no isolation, and in this situation what we do, we insert the isolation cell. Here I have shown the block diagram, and when we insert the isolation cell, the power gated block, whatever the output of the power gated block which is off goes to the isolation cell, and by the operation and by the virtue of the operation of isolation cell, this one is constant. So here this line will contain constant, so it will not be floating as the input. This is the beauty of the isolation cell, and this is how we solve our problematic situation as shown in this infographics with this insertion of the isolation cell. An isolation cell clamps the signal at its input pin to a defined known state, either 0 or 1. Hence, transmission of invalid signal is eradicated. Controllers are used to control and synchronize local power switches and isolation cells with clock gating or power gating signals. So this is another good terminology. Remember, there will be controllers to control and synchronize local power switches and isolation cell. So this is another circuit component there. And two types of controllers are used in VLSI: simple adaptive controller and enhanced adaptive controller. We will not go in very much detail because today our discussion is on the isolation cell, not on the controller. So here in this slide we have explained how isolation cell, that is a special standard cell, tackle the situation of the floating line going from a power gated block into an active block. So we are done with this particular slide. Let's move on to the next slide. Isolation method and isolation cells. When power gating method is applied to a design, in particular mode of operation, we might end up few on domains and few off domains. So this is a cluster of on domains and a cluster of off domains. They were interacting before this particular time when the off domains became really off. Before that they were on. If the outputs of the shutdown domain are connected to the active part of the design, then it might lead to invalid signal transmission and a crowbar current as a result, as we have discussed already. To avoid this, an isolation cell is placed on the output nets of the switched off domain interacting with the active portion of the design. So now here we are taking the broader aspect. We are placing one isolation cell for each of the single instance that we have just discussed in the previous slide. So here is our schematic of isolation cell, or you can call it as a block diagram. So here you can see our power gated block and always on block. This might be another scenario. Always on blocks are also there, and here that means if this block never goes off and this block can go on or off, and here in between we insert the isolation cell. I have used the AND. However, there could be two different type of isolation cell based on the architecture. One is the OR type, another one is the AND type. So here you can see input will be data and isolate bar, and here is the isolated signal for a OR type cell, and for a AND type cell this is data and isolate, and the isolated signal is here. So this is a simple explanation of the two types of the isolation cell generally found in the StdCell package. Any commercial StdCell package can have both of them, so OR and AND. Later we will have some examples. So we are done with this particular slide, so let's move on to the next slide. Detection of missing isolators. The isolation and level shifter strategies are defined at RTL stage itself if the UPF and CPF file. Power management block. This one is digital block, power domain 2, that is analog block with VDD2, and macro with power domain 3 and VDD3. So all these things is designed by the power aware RTL, that is with the UPF or the CPF description. In UPF or CPF, if a isolation and or a level shifter strategy is to be defined between power nets connected to source and sink domains, unable to do so, the resulting in malfunctioning of the design. So if we have missed out any insertion of the isolation cell where it is needed, then this situation might lead to a malfunction of the chip while the chip is in operation. Such scenarios are detected by the standard EDA tools and an error is flagged. So there we have methodologies to detect if any isolators is missing where it should be there. Then the error is flagged by the EDA tool. We're done with this particular slide and let's move on to the next slide. Isolation standard cell example. This one represents the OR type isolation cell, comes under the StdCell package. And this represents AND type isolation cell that comes under StdCell package. The first one you may see with a name like this, ISO-LORX. So here if you see, right, the ISO-L or the ISO represents the isolation cell, and OR here inside the name, ISOL or ISO, okay, this is represent to the isolation, and OR means it is OR type, and X1 is the drive strength. So in the StdCell package, if you browse further, right, either in the documentation or in the actual StdCell physical library, you may find other isolation cell of the OR type with different drive strength like this one and this one. And for the AND type cell, you can see that the name is ISO or ISO-L, and AND is there for the AND type, and drive strength is 1. So if you browse through the physical StdCell library or the documentation of the StdCell library, you might find a different isolation cell with different drive strength, as maybe with this one or this one. So depending upon the design, the StdCell library may contain various drive strength. So don't stick to these names only or this drive strength only. In actual scenario, go to your documentation or the physical library. There you will find different AND or OR type isolation cell with different drive strengths. So we are done with this particular slide. So let's move on to the next slide. Drawbacks and improvements. Here in this slide, we talk about our isolation cell drawbacks and some improvements that we have made already to deal with the drawbacks or backlogs of the isolation standard cells. Isolation cell need to be inserted at the interface of different power domains.
And here in this picture, you can see that here power domain X, and here with the dotted lines, we have separated the three different power domains. Here is power domain Y, PDY and PDZ. Okay. And here is the isolation cell is inserted in the boundary. We also see the level shifter cell. This is just for your information. Right now we are focusing on the isolation cell. So there could be different power domains where such isolation cell has to be placed in the boundary. That means the interface of different power domains. We call it interface because two power domains are physically neighbors. This adds significant area and power overhead. The AND or isolation cells require more area. To lower the area overhead, the isolation cells use NMOS pull-down transistor. Using high VT transistor further lowers leakage current caused by the inactive isolation cells. So here we deal with the power of the shortcomings from the isolation cell design with high VT transistors. So we are done with this particular slide. Let's move on to the next. Summary. Let us summarize whatever we have learned so far in this episode. Conventional techniques are applied to perform electrical checks for voltage crossing domains and power islands. Voltage level shifter, electrical isolation cell, retention cell, etc. The special standard cells are applied in Throuh power aware RTL using PPF or UPF language. Isolation cells, abbreviated as ISO, also this used in the standard cell nomenclature, enable electrically safe power shutdown states from affecting powered on regions by fencing off the propagation of non-deterministic logic states. Two types of standard cell isolators are used, OR and AND types. So here we have summarized our entire discussion in 4 bullets. We are done here with this particular slide. Hey guys, welcome back. In today's episode, we are going to discuss the below points. First, introduction. We will discuss about power, performance and area. We will introduce you to the power, performance and area concept in VLSI. Next, we will go in detail of the power optimizations what are done in VLSI. Next point, we will talk about the performance optimization. Next, we will cover the area optimization. So here we will conclude our episode after discussing all the points, that means power, performance and area. So we will go in detail of each of them. However, we will stay ourselves restricted to the general methods, not to specific any methods of any particular EDA vendors or any specific tool. The general methodologies we will talk through this episode, which are followed in the VLSI domain, and there may be slight variation from one EDA vendor to another EDA vendor in some particular design or domain or some particular area. So that's the menu for today. Without any further delay, let's begin. Introduction. Here we will brief about the power, performance and area, this particular concept in VLSI. The major challenge in VLSI design are area, performance, that is frequency and power consumption. You can understand that nowadays we are going up with the frequency. That means we have already crossed the gigahertz range and we are entering the terahertz range. Today wearable devices are very small and tiny like a smartwatch, and they contain a very less area than the older days gadgets. And power consumption is very important because today we have our devices operated mostly on rechargeable batteries, and the batteries should retain their charge for at least a couple of hours so that you can have your product running for that particular period. Next, in micro-powered battery-operated portable devices such as cell phones, smartwatch, and wearable medical devices, the target is to keep the battery lifetime long and area or weight reasonable. So this is what I have just touched base in the previous line and I was talking. And this is in explicit mode that we have to be there, area should be less, and the battery lifetime, that means the rechargeable battery, should go longer duration as much as possible. Next, in such devices, leakage power during the off state is a major power management concern. So this is a very important thing because when you are having a rechargeable device along with you, probably you can carry it in your pocket or you can wear it maybe in your wrist or some other body parts. So that time when the device is not operating, that means mostly it is in off state, maybe you have switched it off or it has gone to the auto power up mode or maybe in a sleep mode. In that particular time, you have to be very power efficient. That means the device has to save power so that the recharged batteries should run as much as possible.
We already have an entire episode on low power design. I have provided the link in the description, so please go ahead and watch that. We have talked about different type of power consumption from transistor level up to the CMOS level, and all those how are impacting in the VLSI. So here in this particular presentation, I will go for the briefing and comparison of all those methods that I have already talked about there, and we will have a comparison here only. For detailed understanding, please watch this particular episode. Please see the description of this video, get the URL of the video. Next, to chisel higher performance from the same design, various optimization techniques are used. While achieving the timing convergence and gain power, we must not have any negative impact on the overall efficiency. So this is the kind of trade-off we should be looking carefully, and we should be handling it tactically through the design methodologies. Next, analysis and optimization of the overall timing is where necessary to improve the frequency and performance. So why the timing is necessary? Because of the frequency. F is 1 by T by the definition. That means the timing, that the time period and all the violation related with the timings is very much important. In case you are interested, we have an entire series on static timing analysis, and the link is provided in the description, so you can go ahead and see what all errors related to the timings are usually come in the VLSI design and how they are circumvented. Now we are done with this particular slide, and let's move on to the next slide. Power optimization. Here in this particular slide, we'll talk about the general methodologies which are used for the power optimization, and we have an entire episode of the details from the transistor level, power consumption and different power dissipation methods. We are reaching from the transistor level up to the CMOS level, and you can find the link of the video in this video description. Please go ahead and watch. Here we are going to compare the different methodologies we have already talked about, or we may have touch based. So here is a comparison chart. So here in the first column we have techniques. Next we have the dynamic power reduction, then the leakage power reduction, and the other power optimization technique that we are using. So we are talking about power. For detailed understanding of the dynamic or the leakage power and what are the components, please go ahead and watch the video that we have just talked about, and link is in the description. So now clock gating. For this method, the dynamic power reduction comes from the clock gating itself. Next comes the leakage power. So in this methodology, that means in the clock gating, we have to minimize the usage of the low VT cells, that is LVT. LVT stands for low VT cells. These are standard cells. You can have them in your standard cell library. And other power optimization comes from the metal oxide devices, that is the MOS structure. So here we are done for the clock gating part. Now let us go for the power gating. Power efficient techniques, right? We use it for the dynamic power reduction. Next we use the power gating itself, the power gating method itself, for the leakage power reduction. And for other kind of power optimization technique, we use the minimize the capacitance by custom design. Now in case you do not know what is a custom design, we have a full episode and I provide the link in this description, so you can directly jump onto that particular episode to understand what is the custom and semi-custom design methodology in VLSI. We are done here comparing for the power gating. Now we have a variable frequency. In case you are having difficulty in understanding, please go ahead and watch the episode of the low power video that I have just talked about a few minutes ago to understand all these things. Those are in the left hand side. So if we vary the frequency, we do the dynamic power reduction by the variable frequency and leakage power reduction by back biasing. So what is a back biasing? Back biasing means the substrate biasing for the CMOS structure. There is a methodology for providing a back bias. Generally we keep it constant, but however, if we change the back bias, that means the substrate bias of the MOSFET, then the different kind of power reduction comes into place. Basically, the substrate leakage is controlled through the back biasing. And other optimized methods used here is the power efficient circuit design. This is a kind of different methodologies of different houses, that different design houses have different power efficient circuit design methodologies of their own. Once you are in a VLSI company, you will get in detail, but however, you have to keep coming back to this particular episode and going back to your company's methodologies to correlate the things that I am talking about, because in the first slide or in the very beginning of this video, I have talked about that I will touch base the things in a very generic manner, because in different companies, different type of terminologies are used, so that their different trade secrets are kept in a proper way, so that you are tied only inside the company. But however, I cannot go in every company's detail, but here that's why I have touch based in a general format. And once you go there in your company and you come across this kind of terms and you come back to this slide, hear my voice in this video, and then you will be able to correlate very easily. Now next is the variable voltage supply. So first, the dynamic power reduction comes from the variable voltage supply methodologies. Next, the leakage power reduction is achieved by the reduced oxide thickness. That means we engineer the oxide thickness, reduce oxide thickness. Different methodologies are used. Sometimes we use the high K dielectrics, and also all those things are there in the VLSI domain. And for other optimization, it is not applicable here, so we have put NA as an abbreviation to the not applicable. Next, we go for the variable device threshold. That means we vary the VT of the MOSFETs. And here in the dynamic power reduction, we have the variable island. And for leakage power reduction, we use FinFET. Maybe we use a bulk CMOS, or maybe we use a SY CMOS, whatever is applicable. If we have a SY CMOS right from the FinFET, the leakage power would be substantially low. For the power optimization, we do not have anything, so we are marking it with a not applicable, that is NA. So here we are done for the comparison. For the details, please go ahead and watch the low power episode that we have in this FAQ series, and the link is there in the description. So here we are done with this particular slide. Let's move on to the next slide. Performance optimization. So here, this slide and the next slide, I will talk about the timing optimization that is done in the VLSI domain. And again, I am emphasizing that I will talk about the generic methodologies and in generic terms. So in your company, you may have some company specific terms, which your responsibility is to correlate with the things that I am talking about here. First, generally, the timing closure is a combinational effort of first, years spent on the methodology development, script development, sign-off recipe development. So these scripts generally maybe tools accept the tickle, right? Generally, these are the tickle scripts we are talking about, which are maybe easily accepted by the timing tool. In case you do not have a proprietary language for the timing tool, generally this is a tickle, and just for your information, we have an entire series on tickle. If you want to learn it, it's there, and I provide the URL in the description of this video, so that you can directly jump off to the tickle series. Next, we have month of block level and top level final physical implementation. The physical implementation is the physical design part, and there we spend our months because we want to develop, and we have to eradicate more errors in the physical design. We have an entire episode on the physical design. A link is provided in the description. Please go ahead and watch that to understand what are different steps and how the physical design is different in a custom design and in a ASIC design. Here we spend our months to make the physical design part error free from every aspect, and the timing that is the post layout STA has to be very efficient. Next, we have a set of several hundred manual noise and DRC fixes. So these are kind of fixes that we keep on looping back and forth between 2 or 3 steps. That means maybe in layout, then DRC, then LVS, then again layout, then DRC, LVS. Maybe some amount of engineering change order also comes. And along with it, a final multi-day pass of a full chip sign-off analysis and physical verification. So apart from DRC, there are a lot of other physical verification inside the VLSI design to check from every possible angle that the chip could fail. So we have to make the chip fail safe at least for a certain lifetime, so that the customer who's buying the chip, maybe in form of smartphone or maybe in form of a wearable device, that should last for a couple of years. And here in any design house, if you go, this is a generic description. However, you will find the specific things in the company which you are working, or in future you may be working. So next, we have the nature of the timing closure has changed in the technology shrinking. So timing closure before 65 nanometer was different, and after 65 nanometer we are going down, it's coming different, and even below the 10 nanometer it is different. So as we proceed with the step down, that means we are down stepping the technology node, and that changes the timing closure methodologies entirely. During the low power design, HVT cells, that means high threshold voltage and low leakage power, are used. So this is one of the things from the designer that comes, not from the methodologies as we have talked here. So that we use the HVT cells. HVT means high VT. Due to this, transition time increases and it becomes challenging to achieve the timing closure. Now, hence it is important to keep a balanced use of HVT, SVT and LVT cells. So HVT is high VT, LVT is low VT, and this is, I think, super low VT or something. You will find all these terms and their full names in your StdCell library. From the vendor whom you are receiving the StdCell, you should go ahead and ask them what is the meaning of all of them or what is the full form of all of them. So you may have different names from one vendor to another vendor, and these are kind of generic names that I have talked about. Specific names may become different. You have to cross check all of them. So we have talked about performance optimization, that means the timing optimization. As we make the timing efficient, the performance, that is F is equal to 1 by T, that becomes faster. Now we continue our discussion in the next slide. Here we will go through some of the remaining points for the performance optimization, and here it goes. Nowadays, multi-million gate chips are used in order to increase the functionality in digital design. As the number of gates increase, routing becomes complex and in many nets need detour. That means when we are routing, we need to purpose different areas and we have to have a long routing. And now we have a chip that is high terahertz range and we have several million gates there. Detouring of the net adversely affect timing closure of the design. So this detouring may be necessary for the design to act like as it designed, but however it impacts the timing. A good floor plan is used to avoid congestion, nets detouring to achieve timing closure. That means with proper floor planning, we avoid congestion. That means do not pass all the lines from same area. That means it becomes congested, and we avoid net detouring in this way. And this helps in the good timing closure. That means a higher performance. Crosstalk delay and noise are dominating, which affects the timing closure adversely. By double spacing between the aggressor and the victim and shielding, crosstalk can be done. Here we are done with this particular slide, so let's move on to the next slide. Area optimization. So here we will talk in brief details about the different area optimization methodologies, and again I am emphasizing I will cover in a generic manner. Company to company specific measures or methodologies will be there, and sometimes these methods are very secret to the company's success, so you should not disclose them to the public, and this video is for learning purpose, so you can come back to this video and correlate the methodologies for understanding. Area optimization. Area optimization does not always mean area shrinking. This is the term, first of all. It's not that we are shrinking the area every time. We are optimizing it. That means we have to get an optimum area so that the design is properly functional, performance is there, good, leakage power, dynamic power, etc. All those things are there. So area optimization does not mean always the area shrinking. It means optimization. Next, source code modification. RTL description style is done as synthesis tools are very sensitive to the coding style. You can see at RTL level, we can also do something for the area optimize as we pass through the synthesis tools, because different synthesis tools are having different algorithm inside them. Identify static signals, that is register enables, and simplify them. Next, pack the register with orphan logic that were inferred as standalone gates by the ASIC synthesis. So in your company which you are currently working, or in future whatever company you will be working, you will find some of them or all of them or different methodologies altogether. Don't panic, because this is a general guideline and there can be a variation, because the technology world in VLSI is a super fast changing area. Floor planning is the first step for the back-end or physical design in VLSI design flow. As I have mentioned in the video description, you will find our full episode on physical design. There you will have the details why this is the first step. Next, it is a design step to estimate chip area and wear length by considering the optimal placement of digital blocks and their inter. In addition to that, I would like to speak that today's world of VLSI chip design, lot of macros, that means we purchase block from other companies and we directly implement in our system. So these are hard macros, maybe these are in layout format already and you cannot change. That also you must consider while you are optimizing the area. Next, we have the classical floor planning methods that are normally used to increase packing density, minimize the total chip. There are some classical methods, there are some advanced methods nowadays which are used for the packing density to be optimized, and that should minimize as much as possible, obviously, for the chip area. They do not consider the chip boundaries, that is the outline, but modern floor planning methods deal with fixed outline floor planning. These are methodology things that you will find in your company or in future whatever company you will join, assuming that right now you are a graduate. Floor plan also needs to consider whether there is sufficient routing area between the blocks so that the routing algorithms can complete routing tasks without experiencing congestion. We talked about the congestion, right? The dealing with the congestion is right at the floor planning stage, and this is one thing that the area optimization we need, because we need to manage everything. That means there is the macros, we need to standard cell, we need to place our tissue blocks, everything, and at the same time we should not have congestion. That means one area is too much dense and another area is too much less dense. So everything should be balanced, and that is the purpose of the area optimization. And at the same time we need our timing performance, that means the performance of the chip, as well as all sort of power are in check. So here we are done with our area optimization, and in today's episode we have covered all the types of optimization. I have touched base in a very generic manner because these methods are trade secrets of a company, and every company want to keep them secret, so they are winners in the market. This episode is for education, so generically I have speaked here, and your company which you are right now working on, maybe in future working, assuming you are a graduate, you will find your own knowledge, your own working knowledge there. So this is a video for the beginners, assuming you are a graduate, to understand what is the power, performance and area optimization in VLSI. So here we are done. Let's move on to the next slide. Thank you very much for watching up to this point, and don't forget to like, share and subscribe. In case you have some dislikes, put that as in words in the comment section down below, and bye for today.